Should you enter a lottery? Question. That one's easy because we all know the answer is always no, because the people running the lottery know how to do utility theory too. But it's a good getting started example. Here I talk about how to build trees. I walk you through an example of should you send a coupon to these customers. Here I do an example of continuous probabilities. Let's talk about that really quickly. Let's suppose that you have a branch of uncertainty, meaning there are three things that could happen. If there are three things that could happen, then the probabilities must sum to what? 1. So what's the probability of this branch? It has to be 0.5, because if it were something else, it would not be a distribution, right? Okay, well, if we knew the utilities of each of these cases, 1, 2, and 5, what's the utility of being up here? 0.2 times 1 plus 0.3 times 2 plus 0.5 times 5. And because those numbers sum to 1, you're getting one full dose of utility in your final computation that you put up here, right? Okay, what if your choice is continuous? So here you are at the top of some tree, but in fact, there's a whole spectrum of choices you could make. And the utility is, meaning C represents the choice you can make, and the utility that you get from it is some function of that choice. Then how do you make that decision? Yeah, exactly right. So, you know how in math when you take calculus, they keep saying, what's the area under the curve? And the way you measure the area under the curve is you kind of discretize it, and you sum up the areas of all of these squares. And that's really symbolic because you take it in the limit to where the size of those squares is infinitely small. That's what an integral is. Well, that's the same way you do this, is you just marginalize over the probabilities of all possible things in the distribution. So now imagine, instead of there just being 3 choices, there's some arbitrarily large number of choices, and the marginalization is just multiplying the probability of each of those choices by its utility. So essentially you integrate over the equation for the probability distribution, and you will be able to compute exactly the right value, even though it's continuous, of the choice that maximizes utility. Do we need an example, or is that enough that basically if you remember your calculus, you're good? You're good. I think I'll just leave it at that. I do want you to understand it, but I'm not going to be demanding that you do continuous integrals in this class, just because a lot of you have already forgotten your calculus, and I don't want to have to hear all the whining. So there's that. But can you see that you can do continuous probability distributions just as well as discrete ones? So I do an example of a continuous one there where we do an integral. And in this case, we're computing whether or not to send a rocket to Mars or something like that. Do you think NASA actually does utility value computations? Yeah, you bet they do. When people drill for oil, do you know how they drill for oil? They actually set off an explosion in the ground, and then the explosion sends an echo that ripples down through the ground. And it turns out that those shock waves, bounce off of oil differently than they bounce off of rocks that are underground. So they put these seismometers all over the ground, and they look at the seismometers and analyze them with machine learning, and they get these probability distributions. And those probability distributions tell them how likely there is that there's oil under the ground. But do they ever know there's oil? Never. They always get probabilities, and they're usually things like, there's a 1 in 50,000 probability that there's oil here. Should they drill? Maybe. It costs $10 million to drill, but if they do, and there's oil with some low probability, then there's $1 billion of payoff. So what do? Utility theory, and then you compute whether it's the right decision, and if it is, then they do it. And if you maximize utility enough times, it'll pay off enough times, and eventually these oil companies get rich. Are oil companies rich? You bet they are. It's because they know how to do utility theory. Same with NASA. If they're going to pay $10 million to send a rocket to the moon, they want to know the odds of success and the odds of bad things happening. And even if you have to guess at some of the values, at least you can make good decisions. Here I give an example of, should you eat a death cap mushroom? Or rather, should you eat a mushroom you find in the woods? By the way, the answer is no. I think I used that one to compute the value of your life. So that was kind of the example of my pizza one. And one thing I love to do on tests is I ask a problem to you, I describe some situation and I say, and then I throw in a bunch of superfluous details that have no bearing on the problem. And then I see if students can filter out the things they actually needed from the things they don't and compute the right decision to make. And here's an example of that. Why do I do that? Because I'm a jerk. And because that's very real world, isn't it? You'll never work for a company that says, here are the 3 values you need. Please compute the right answer for us so we can make a good decision. You're the technical person who's smart and knows how to solve problems, so they'll just describe the situation to you and they won't even give you enough information. And you'll have to go hunt down the information you need and then tell your boss, hey, it turns out that not sending the coupons is better than sending them. And then your boss will say, wow, thanks, you saved us $50 million, and they'll be really proud of you and they'll be glad they invested in an AI expert. So brush up on some of these practice problems before you take my midterm. And then that branches into some other topics we're not going to cover in this class. Actually, I just thought of one other thing I do want to cover just because I can. Then I'll get into GAs. Okay. Let's suppose you wanted to simulate a situation. In fact, let's do this one. You want to draw a random value from this distribution because you want to create a world that follows this probability distribution. How would you draw a random value that makes these choices according to these probabilities? Do you understand the question? I'm saying your choices are A, B, and C. I want you to draw a random choice, A, B, or C, and I want 2/10 of the time for your choice to be A, and 3/10 of the time for your choice to be B, and half of the time for your choice to be C. Write some code that will do this. Ready, set, go. Think about it and see if you can come up with an answer. The first thing I would do is I would take these values and compute the cumulative distribution. So we're always going to start with a 0, add 0.2 to that, add 0.3 to that, add 0.5 to that, and that's a 1. Turns out this 0.5 is not the same as that 0.5, but it happened to work out because these add up to 0.5. And so I think what you said was technically right. Then I would draw a random number from 0 and 1. By the way, how do you draw a random number between 0 and 1 in, say, Java? Use the random class, and there's an operation called next double, and that gives you a random number between 0 and 1. Every language will have an operation for that. Okay. Then I would find the smallest value, the smallest number in the cumulative distribution that's less than the random number I drew, and that tells me which choice to make. In this case, it is this 0.5, so you got it. And that tells me that I should choose, I think it was this one. Okay, there you go. It's unfortunate that those numbers added up that smoothly. Just to make that not happen, let's say they were 0.1, 0.2, and 0.7. Now the cumulative distribution is going to look more like 0.1, 0.3, and 1. And if I drew a, say, 0.6 from my random number generator, which one should I do? Well, do this one because it's bigger than both of those numbers. Okay, and essentially this same technique also works with the continuous distributions. If you want to draw a random value from some probability distribution that you have a continuous value for, how do you do it? Well, first you compute the cumulative distribution. 1, compute cumulative. 2, draw a random value from a uniform distribution. 3, run it through the inverse cumulative distribution, and that will give you a number from the distribution itself. Okay, there you go. I've told you how to draw a random number from any arbitrary distribution.